Hello, space enthusiasts! Today, we're diving into one of the universe's most captivating and enigmatic phenomena, black holes. What exactly are they? Imagine a region in spacetime where gravity is so incredibly strong that nothing, not even light, can escape its grasp. Sounds pretty wild, right? But how do these cosmic monsters come to be? Well, their story begins with the dramatic lives and deaths of the biggest stars in our universe. It's a tale of immense power, fundamental forces, and mind-boggling densities. Let's start from the very beginning, with the most important ingredient, gravity. At the heart of black hole formation, and indeed the entire universe, is gravity. Gravity is an invisible force that pulls objects with mass or energy towards each other. The more mass an object has, the stronger its gravitational pull. Think about how the Earth orbits the Sun, or how you stay on the ground. That's gravity at work. In space, gravity isn't just a gentle tug, it's a powerful sculptor, shaping galaxies, forming stars, and eventually, creating the conditions for black holes. It's the constant force that drives everything we're about to discuss. Before we get to black holes, we need to understand stars. Stars are gigantic, luminous balls of plasma, primarily made of hydrogen and helium, held together by their own immense gravity. They're like the universe's natural fusion reactors, constantly burning fuel and releasing incredible amounts of energy as light and heat. Our own sun is a star. But not all stars are created equal. Their size, mass, and how they live their lives determine their ultimate fate, and for some, that fate is a spectacular, violent collapse into a black hole. So, how do stars shine? Through a process called nuclear fusion. Deep within a star's core, immense gravitational pressure and incredibly high temperatures force atomic nuclei, primarily hydrogen, to fuse together to form heavier elements, like helium. This process releases a tremendous amount of energy, which creates an outward pressure that perfectly counteracts the inward pull of gravity. It's a delicate cosmic balancing act. As long as a star has enough fuel for fusion, it remains stable, shining brightly for millions or even billions of years. But what happens when that fuel runs out? Every star, and therefore every black hole, begins its life in a stellar nebula. A nebula is a colossal cloud of gas, dust, and plasma scattered throughout space. These magnificent cosmic nurseries are made mostly of hydrogen, helium, and tiny amounts of heavier elements. Imagine vast, swirling, colorful clouds that stretch for light years. Within these nebulae, gravity slowly starts to pull clumps of gas and dust together. As more material accumulates, the clump grows denser and its gravitational pull strengthens, drawing in even more matter. This is the very first step in making a star. As gravity continues to pull material inward within a nebula, the clump becomes a protostar. This is essentially an embryonic star, not yet hot enough for nuclear fusion to begin in its core. It's still gathering mass, and the increasing gravitational pressure makes its core hotter and denser. Think of it like a giant cosmic snowball rolling downhill, getting bigger and more compressed. This phase can last for hundreds of thousands to several million years, slowly building up the conditions necessary to ignite the star's nuclear furnace. It's a waiting game, but one with an explosive payoff. Once the protostar's core reaches a critical temperature and pressure, nuclear fusion ignites, and it officially becomes a main sequence star. This is the longest and most stable phase of a star's life. Our Sun is a main sequence star, happily fusing hydrogen into helium in its core. During this stage, the outward pressure from fusion perfectly balances the inward pull of gravity, creating a stable equilibrium. How long a star stays on the main sequence depends entirely on its mass. Smaller stars burn their fuel slowly and can last for trillions of years, but massive stars? Their lives are much shorter and more dramatic. Now, here's where black holes enter the scene. Only the most massive stars, those at least 8 to 10 times the mass of our Sun, have the potential to become black holes. These stellar giants burn through their nuclear fuel at an astonishing rate due to their immense gravity, which creates even higher core temperatures and pressures. While our sun will live for billions more years, a star 20 times more massive might only shine for a few million years. They live fast and die young, but their deaths are truly spectacular, setting the stage for one of the universe's most extreme objects. As a massive star starts to exhaust its hydrogen fuel, it moves into its next phase, a red supergiant. The core contracts, heats up, and begins fusing helium into heavier elements like carbon and oxygen. This intense heat causes the outer layers of the star to dramatically expand and cool, turning it into a vast, luminous, reddish giant. Imagine a star so big that if it were in place of our Sun, its outer layers would extend past the orbit of Mars or even Jupiter. Betelgeuse is a famous example of a red supergiant. But this expansion is just a prelude to its ultimate collapse. Inside the core of a massive red supergiant, a series of fusion reactions create progressively heavier elements, carbon, oxygen, neon, magnesium, and so on, building up layers like an onion. Each new fusion reaction requires higher temperatures and pressures, and produces less energy. Eventually, the star reaches its limit. It starts to produce iron in its core. Fusing iron actually consumes energy instead of releasing it. This is a critical turning point. Once the core is primarily iron, the star has no more fuel left to burn, and the outward pressure from fusion suddenly ceases. Gravity, unopposed, begins its relentless work. With no more fusion to counteract gravity, the star's iron core begins to collapse inward at an astonishing speed. In mere milliseconds, a core many times the mass of our Sun crunches down to an incredibly dense object just tens of kilometers across. Imagine something the size of Mount Everest being squeezed into a thimble. The atoms themselves are crushed, electrons are forced into protons, forming neutrons. This process releases an unbelievable amount of energy. The outer layers of the star suddenly have nothing to support them and also fall inward, slamming into the now incredibly rigid, dense core. It's an unimaginable cosmic catastrophe. When the inward falling outer layers of the star hit the superdense, rigid core, they rebound with tremendous force, creating a colossal shockwave that blasts outward. This is a Type II supernova, one of the most powerful explosions in the universe. For a short period, a supernova can outshine an entire galaxy. It releases more energy than the Sun will produce in its entire 10 billion year lifespan. This explosion scatters most of the star's material, including all those heavy elements created during fusion, back into space. These elements then become the building blocks for new stars, planets, and even life itself. But what's left behind in the core? What remains after a supernova depends on the original mass of the star's core. If the remnant core is between about 1.4 and 3 times the mass of our Sun, it collapses into an incredibly dense object called a neutron star. Imagine squeezing a star with more mass than our Sun into a sphere only about 20 kilometers wide, the size of a city. A teaspoon of neutron star material would weigh billions of tons. Neutron stars are astonishingly dense, but they're still able to resist further collapse due to a quantum mechanical pressure called neutron degeneracy pressure. However, if the core is even heavier, this pressure isn't enough. This is where the black hole comes in. If the leftover core after the supernova is more than roughly 3 times the mass of our Sun, even the immense neutron degeneracy pressure isn't strong enough to halt gravity's relentless pull. The core continues to collapse inward, past the point of being a neutron star, and keeps on collapsing, getting denser and denser, until all its mass is compressed into an infinitesimally small, infinitely dense point called a singularity. It's here, at this singularity, that the laws of physics as we know them begin to break down, and a true cosmic anomaly is born. Let's zoom in on this mind-bending concept, the singularity. At the heart of every black hole, according to current understanding, lies a singularity, a point of infinite density and zero volume. All the mass of the collapsed star is crushed into this single point. It's difficult for our brains to even comprehend something so extreme. Imagine taking Mount Everest and crushing it down smaller than an atom. Now imagine taking an entire star and crushing it even further, into a point smaller than anything you can imagine. This is the ultimate fate of a massive stellar core, a place where gravity is so dominant it defies comprehension. Surrounding the singularity is an invisible boundary called the event horizon. This is not a physical surface, but rather a theoretical boundary in spacetime. Think of it like a cosmic waterfall. Once you cross the event horizon, there's no going back. The escape velocity, the speed you need to travel to escape an object's gravitational pull, at the event horizon is equal to the speed of light. Since nothing can travel faster than light, anything that crosses this boundary, including light itself, is trapped forever. It's the ultimate one-way trip into the unknown. The black holes we've been discussing, formed from the collapse of massive stars, are called stellar mass black holes. They typically have masses between about 3 and several tens of times the mass of our Sun. These are the most common type of black holes in the universe. We've detected many of them through their interactions with companion stars, where they pull material away, causing it to heat up and emit X-rays. They're scattered throughout galaxies, including our own Milky Way, silent cosmic devourers born from the spectacular deaths of some of the universe's most brilliant stars. They are a profound testament to the power of gravity. To recap, let's quickly compare the two main remnants of massive stars. On one side, we have neutron stars, which are incredibly dense but still have a physical surface, resisting gravity with neutron degeneracy pressure. They are like cosmic jewels, spinning rapidly and often emitting beams of radiation. On the other side, if the core is even heavier, we get black holes. Here, gravity has completely won, collapsing the core into a singularity surrounded by an event horizon. They are fundamentally different objects, both born from supernova explosions, but representing different extremes of density and gravitational power. While stellar mass black holes are born from collapsing stars, it's worth noting there are other types. Supermassive black holes, for instance, reside at the centers of most galaxies, including our own Milky Way. Sagittarius A* in our galaxy is over 4 million times the mass of our Sun. Their formation mechanism is still an active area of research, possibly involving the merger of many smaller black holes or the direct collapse of massive gas clouds. Then there are also intermediate mass black holes, sitting between stellar and supermassive sizes, which are also quite mysterious. The universe truly has a diverse family of these gravitational behemoths. How do we even know black holes exist if they don't emit light? We can't see them directly, but we can detect their presence through their powerful gravitational effects on surrounding matter and stars. We look for stars orbiting an invisible, massive object, or for X-rays emitted by gas heating up as it spirals into an accretion disk around the black hole. We also use gravitational waves, ripples in spacetime generated when black holes merge, to confirm their existence. These indirect observations provide compelling evidence for these cosmic giants, helping us map the invisible architecture of the universe. So there you have it, the incredible, dramatic journey of a massive star, from a cloud of gas and dust to its ultimate, spectacular demise as a black hole. It's a testament to the sheer power of gravity and nuclear forces, shaping the cosmos in ways that continue to astound us. Black holes remain one of the most extreme and mysterious objects in the universe, pushing the boundaries of our understanding of physics. Every new discovery about them unlocks deeper secrets about space, time, and the very fabric of reality. The universe truly is a wondrous place, full of surprises. Thanks for joining us on this cosmic adventure.